is take a few moments to kick off our chapter on infrared, which is chapter 12. Now, we're always in a little bit of a dilemma here. How many of you have had some infrared spectroscopy before? All of my students have. I've been there the last semester. I did. But for people that haven't had 235 with me, this may be a fairly new topic. And we're going to go through it fairly quickly because we don't have the luxury of going through it in detail. So what you're going to need to do is go to the textbook and read more elaboration on some of these concepts. All right? And I know this is not all hands went up, so I don't want to embarrass you if you haven't seen a lot of spectroscopy. It's really important. In the modern organic laboratory, unknowns are identified almost exclusively by spectroscopy, the infrared being one of the techniques. In the laboratory this semester, you're going to identify some unknowns by classical techniques, by chemical reactions, which I think is really instructive, and you'll probably enjoy that portion of the laboratory. But even if you don't, just recognize you're being taught a whole bunch. But the real organic chemist uses this technique to identify known compounds. All right? Now, spectroscopy is a technique that involves interaction of matter or material or the substance under study with radiation, electromagnetic radiation. Most of the techniques are non-destructive. In other words, the sample's not destroyed in the test. Absorption spectroscopy it measures the amount of light absorbed as it passes through a sample of your compound. The kinds that we'll encounter in the organic chemistry lab are listed here. Infrared is very important. It's listed right at the top. We measure the amount of infrared radiation that's absorbed as we scan the range of infrared based on bond energies. It turns out, what does infrared do to a molecule?
Causes it to vibrate.
Causes bonds to vibrate. And it turns out that the energy that is required to cause a bond to vibrate is based on the bond energy itself. So a carbon-carbon single bond will vibrate at a certain energy. A carbon-carbon double bond will vibrate at a higher energy because it's a stronger bond. In other words, infrared changes based on bond energies. And so what we can do is we can scan through a range of infrared frequencies or energies, and we can see what kind of bonds are present in our sample. Carbon-hydrogen bonds, carbon-oxygen bonds, oxygen-hydrogen bonds. They all absorb in typical regions of the spectrum. And so a scan of the infrared frequencies or wavelengths tells us what kinds of bonds are present in our sample. That's the bottom line. Another technique that's usually lumped in, and it's actually part of chapter 12 with spectroscopy, is a technique that's not spectroscopy. It's called mass spectrometry. And in this particular technique, we take a particle or a substance under study and we hit it with a high energy beam of electrons in a high vacuum, and it shatters. It falls apart into fragments. Many of the fragments are charged, and then we put them under the influence of a magnetic field, which draws them through a chamber and sorts them. And we can see those different fragments, and a fragmentation pattern is very characteristic of a particular molecule. Usually the analysis of this particular technique is done by a computer with a memory, with a whole bunch of spectral patterns in it. Of all of the techniques for identification purposes, this is the gold standard here. We don't have one of these for ready usage here, but recognize this can be used in court, it can be used in a whole variety of applications. And generally, if someone said this compound was identified by mass spectrometry, there's usually no question asked. It's pretty rock solid. So far, so good? We'll look at it as part of chapter 12. It won't be something that we'll do in the laboratory. You do have access to an infrared in the laboratory, which you'll be able to use. NMR, nuclear magnetic resonance spectroscopy, is based on the fact that nuclei that have an odd number of protons or an odd number of neutrons or both have a magnetic moment associated with them. And in a powerful magnetic field, they will precess. They'll rotate in that magnetic field and create their own little magnetic field as a consequence. This only happens noticeably in very powerful magnetic fields, many thousands of times more powerful than the Earth's magnetic field. So this needs to be done in a powerful magnet system. But once I get these nuclei rotating or precessing in a magnetic field, it turns out that they can have two states, a positive state, we call a positive state and a negative state. And they can be caused to jump back and forth between those two states if I hit them with a certain energy of radiation, electromagnetic radiation. And that's what the resonance is called. I find just the right energy and I can cause these nuclei to flip back and forth between the two orientations. And that again is an indication of the environment that those nuclei are in. And this, for normal purposes, is usually the most instructive in terms of what the structure is. Now, if we have a mass spectrometer with a library of spectral patterns or fragmentation patterns, no need to worry about it. But generally, an IR and an NMR together are enough to identify a compound. And you'll work with, we're actually looking at buying an NMR for the college, but we have an IR downstairs that we use on a routine basis. All right? Now, finally, ultraviolet spectroscopy is a technique that we'll look at, but not until about chapter 15, 16, in that range. And it turns out that when we have multiple double bonds present, they will absorb light radiation or radiation in the ultraviolet, and we'll be able to make some generalizations about the structure based on their ultraviolet behavior. All right? So far, so good? Just a couple of review concepts. If we look at electromagnetic radiation, we recognize, or we should recognize, there's two components. There's an electrical component and a magnetic component. And they are at 90 degrees to one another. What we're looking at here is the electrical field oscillation, which is usually represented with a sine wave. And recognize that as this, if there's a stationary observer here, let's say, as this wave front passes the stationary observer, I see a moment where the oscillation is in the positive phase and a moment where it's in the negative phase. And so this stationary observer experiences this fluctuation in electric field. Does that make sense? Positive and then negative. At the same time, which we can't show you on the slide, there's a magnetic field 90 degrees away where there's an oscillation as well. And we generally don't take advantage of that, but the electrical field oscillation will be used to excite the molecule in infrared. All right? What does lambda mean?
Wavelength.
Wavelength. It's a Greek L for length. Now, some formulas that are frequently used with photo systems. Speed of light is equal to lambda nu, wavelength times the frequency. Frequency, this symbol here called nu, is a Greek n. It refers to the number of cycles per second that the light exhibits, its frequency. Okay? And I don't know why in the early days of working through these formulas, they elected to use Greek letters, but lambda means wavelength, and nu means number of cycles per second. N and L, that's why. Now, it turns out that if I know, since the speed of light is a constant, particularly in a vacuum, if I know one of these, I can calculate the other. In this particular case, we're calculating the wavelength based on knowing the frequency. Notice also, how are wavelength and frequency related to one another? Inversely proportional. So as the frequency increases, what happens to the wavelength?
Decrease.
It decreases, so the wavelength gets shorter. So short wavelength light is high frequency light. Long wavelength light is low frequency light. Does that make sense? Okay. And a relationship that Einstein and Planck developed says the energy of a photon of particular electromagnetic radiation is equal to Planck's constant times its frequency, which tells us that energy and frequency are directly proportional. Okay, And in fact, the proportionality constant is Planck's constant, which is this down here. Now, generally in infrared spectrum, the report out, the wavelengths are actually not reported in either frequency or wavelength. They're, strangely enough, reported usually in reciprocal wavelength. In other words, I take the wavelength of the light in centimeters and do its inverse. Don't ask me why. I wouldn't have chosen to do it that way, but that's how it's done. Now, some spectral characteristics with respect to the electromagnetic spectrum. Gamma rays, highest energy, then X-rays, then vacuum UV, near UV. Some of this spills over into the atmosphere, into the Earth. It gets through the ozone layer. And sunburning and sun tanning are largely due to this narrow band of near UV that actually managed to get through the atmosphere and reach the Earth. Then we have the visible region, which is actually fairly narrow. The infrared that we're going to be talking about today is just beyond the visible to the low energy end, then microwave and radio. All right? Pretty wide range, and what you can actually see, the visible region, is actually a pretty narrow band. Recognize that this is a log scale here. This is a power of 10 scale, so it sort of overemphasizes how wide the visible range really is. Oh, and effects. The high energy radiation tends to cause ionization. You've heard ionizing radiation?
Mm-hmm.
You ever heard that?
Yeah.
That's the bad kind. That's so much energy that when it strikes a biological molecule, it breaks bonds and causes ionization. And those ionized substances can participate in unfortunate reactions like enzyme denaturation, DNA mutation, and things like that. So experience, we like to minimize our exposure to strong ultraviolet, X-rays, and gamma rays for that very reason. Okay. Now, beginning in the near UV through the visible region, we excite electrons, but we don't break bonds. We don't ionize, but we just excite electrons to higher energy orbitals, and then they come back down. And so this is a region where we see a lot of useful things happening with light, but we don't actually create as much danger associated, or there's not as much danger associated with it. For example, this might be what we would look at this for chlorophyll. In photosynthesis, in a chlorophyll molecule, we strike the chlorophyll molecule with electromagnetic radiation in visible range, or region, and an electron is excited to an excited state. Normally, it just comes back down by re-radiating the emission, or emitting the radiation again, or by vibrating and losing its energy thermally. In chlorophyll, what does it do? Do you remember biology? What does a chlorophyll molecule do with the energy it's absorbed? It accepts energy and excites an electron to a high state. What does it do with that? It actually passes it on to a molecule. So the electron's actually lost. There's actually an electron transport chain associated with photosynthesis. And so normally when you excite a molecule, the electron goes to a higher state and then comes back down by releasing the energy in various forms, sometimes by re-emitting light, sometimes by vibrating and bumping into its neighbors and releasing the energy by heat. But in the case of chlorophyll, there's a molecule there that accepts the electron, the excited electron, and ultimately as the electron goes down through a cyclic, I feel like I'm telling you